right. Thank you, Stefan, for introducing me. So I would like to show you an overview of my PhD research, which focuses on the optimization and visualization of numerical models of flash floods in steep Norwegian rivers. The main motivation why I want to focus on optimizing models is because, and then later on visualizing them, is because we would like to work on presenting more relatable or more in a more user-friendly way results of flood risk to the population, and we would like to engage them a bit more. And it's quite challenging, but I think it would be quite interesting to create a game where we can present several scenarios, and the user can actually play around and learn something through the game. And so to do so, we would need very fast models that could iterate or compute along the way, so in real time while the user plays. Well, no one likes to wait while playing, so we need very fast ones. I don't know how fast we can get, but we're working on it. So one thing that we have done is that there was a recent flood 3 years ago. There was a small village in the west of Norway that flooded, and we were lucky enough to document the flood in the field. And although the catchment is very small, let me see if I can, yeah, here I have a laser pointer. Although the catchment is very small, it's 25 square kilometers, and we focused only on the most downstream ridge, which was 700 meters long, because it's where the population is agglomerated. We have tried to have a 2D model that is very fast in this small test case. And we have tried parallel CPU computing. We have tried both single thread and multi-thread and of this 2D hydrodynamic model. And we have done so also on GPU. And we have explored a bit with machine learning. We have simulated a 1D convolutional neural networks model. Although the data is still to be analyzed, I can show you a small, short sneak peek into the comparison of the performance of CPU computing time versus GPU computing time. You can see this in the figure B. So the blue bars are GPU computing time, and you can see that they are much lower than the CPU computing time. And it's on the order of several seconds, it's less than 10 seconds per time step. And whereas on CPU, the red bars are the single thread, and the green, black, and orange bars are the multi-thread. They are much higher, they are much slower. But we also have learned that the dispersion of the data is obviously, as seen here, much larger on the CPU models than on the GPU computed models. Now, one thing that we have noticed is that we have obviously more threads on a GPU than on a CPU. We had up to 4,000 threads on a GPU sometimes, whereas in most of the CPUs that we tested, we had less than 8 threads. So obviously the number of the threads that are available in the processing unit will condition how fast the model can be. Now, we wanted to also compare these GPU results, which were obviously faster than the CPU ones, with machine learning model, but we don't know yet how reliable the test was. So although this has to be, still processed and analyzed, I remember that the machine learning model was faster, although the learning in the training process was very slow. Now we need to also analyze, of course, the position of the data. It would be interesting to have a model that also shows where we could protect the river and protect the population, so decision makers can also use this game to obviously make decisions. And that's it. That will be basically future work. We would like to test these things. Thank you very much. If you want to know more about the project, you can scan this code here, and a bit more about my research is in the other codes. Thanks.
Thank you, Adina, for the very interesting talk.